So before we go any further, here's some small examples that'll help illustrate exactly what I'm talking about. And these are related to the geometric problems we looked at just a minute ago. That is, if my function is a constant k, I want to know, first of all, if I'm looking for the antiderivative, usually we call that capital F, then I'm looking for the function whose derivative gives me k, right? And if you think about it, the derivative with respect to x of x is 1. So if I have a constant multiplied by x, that'll work. Look, if we have k times x, if I take the derivative of this, the k is just a constant, it stays there, but the derivative of x is 1. So in fact, it gives me this. So capital F is the antiderivative of small f, because when I take the derivative of that, I get little f. Similarly here, if I have x, this now we have to think about the power rule, right? Well, we just sort of take the power rule and go backward. That is, if I'm looking for a function whose derivative is x, I think to myself, well, whenever I do the power rule, remember, I take the power, I bring it down to the front, and then I subtract that power by 1, right? Reduce it by 1. So I'll just do the opposite. Instead, there's my base. I'm going to add 1 to the power. Well, here it's 1. If I add 1, I get 2. And the point is, when I take the derivative, I have to bring that 2 down, so I have to sort of do the opposite of that. Well, the opposite would be a fraction with a 2 in the denominator, right? So if I put a fraction of 1/2 here, that takes care of the fact that when the 2 comes down, I actually should get a 1 for the constant out front, right? The coefficient. So in fact, I now have the antiderivative. That is, the derivative of this capital function, f, capital F I should say, really does give me my lowercase f. And in fact, it works. If you take the capital derivative of this capital F in both cases, I get my lowercase f. And therefore, this is the antiderivative. Okay, usually we, again, denote it with capital F. So before I go any further, we have to make one other note. That is, even though I claimed that we found the antiderivative, we have to be careful. We really found one of the antiderivatives of the functions we were looking at before. And here's the key. Even though this is certainly the antiderivative that we found a minute ago, it's not really the only antiderivative. And the reason why is because the derivative of any constant is 0, right? So in fact, even though this is one antiderivative, another antiderivative might be, what if capital F of x were 1/2 x squared plus 4, right? If I take the derivative of this capital F, I still get x, right? Because the derivative of 4 is 0. And that happens for any constant, whether we add it or subtract it. So the point is that we have to be a little bit more careful when we're looking for antiderivatives, because we're not going to get an individual antiderivative. We have, in fact, an infinite class of antiderivatives. It's a whole class of functions. There's a lot of them. And usually when we ask the question, I want the antiderivative or I want an antiderivative of a given function, we'd be okay with one of them. It doesn't really matter. However, we can sort of kill all the birds with one stone if I just call this constant k, right? If I throw a k there, that means it'll work for any k, even if k is negative. So really, the antiderivative for this would be all the functions that look like this. In the last example, I did show you an antiderivative, but it was when k was 0. So to be more careful, we have to realize that, in fact, the antiderivative, there's a whole lot of antiderivatives of any given function. Okay, so really what we want to do is always add an extra constant, because it'll work for all constants. And that really would be the whole class of antiderivatives for this given function. Now, putting all of that together, we can finally write down the proper notation for the antiderivative. That is, if we're really looking for the antiderivative, and in fact, we have that capital F is the antiderivative of f. That is, it's the function whose derivative gives me the lowercase f. Then we have the following symbol. We write this sort of elongated s to indicate that we're looking for the antiderivative. And we say that this elongated x, put a little dx here to indicate the variable that we have. This should equal your capital F plus any constant k. Usually, you'll see that the constant is written as c. It doesn't really matter as long as it's a constant. I'll go with c because that's more common. But really, this is the proper notation for looking for the antiderivative. That is, we write, if we're looking for the antiderivative of lowercase f, we put it in between an elongated s and a little dx here. Okay? And this tells us that we're looking for the antiderivative. And if capital F is indeed the antiderivative, this is how we would write it. Okay? And we should say for any constant c. Right? So this is our final definition with all of the proper symbols for the antiderivative of my lowercase f.